The next closed domain method we will look at is called the method of false position or regular falsi. And the idea is an improvement on the bisection method. We still need a bracket around the root, but rather than finding the midpoint, we instead connect the 2 points with a straight line and then find the intersection of that straight line with the x-axis. And that intersection point would be our new point, our new part of our new refined bracket. So let's see how this works. We take this same function that we used earlier. We have a and b. I'm bracketing the root. Then next step, we draw a line between a and b. Now that line intersects the x-axis at the point C, and then our new bracket would be C and B. Now here's an activity for you. The line between a and b has a slope of m equal f of b minus f of a over b minus a, rise over run. Given that, find a formula for the point C, for the location of C, as a function of m. Press pause, take a couple minutes and see if you can deduce that by yourself. Okay, here's my solution. The line connecting a and b has the formula y equal mx plus q. We know m, that's the slope, but we do not know q, that's the intercept. Okay, now the intercept can be found by evaluating the line at either x equal a or x equal b. For example, at x equal b, we have y of b equal mb plus q equal f of b. So we know m, we know b, we know f of b, we can solve for q, and therefore q is f of b minus mb. We could do the same with a, okay, with x equal a. It will, the results will be similar. The point C now is where the line intersects the x-axis, or y of c equal mc plus q, so that's x equals c, equals 0. Now in this case we know m, we know q, we don't know c. We solve for c, we get c equal minus q over m. We substitute, you get c equal b minus f of b over m. So that gives us the new point in the interval. Now we check for convergence. If f of c is less than or equal to tolerance, we stop. Otherwise, start with a new bracket. Now our c, in this case, because it's to the left of the root, it becomes the new a. B remains the same. Then we draw a new line, and then when that line intersects the x-axis, that's going to be our new c. We check for f of c, and so on and so forth. And the algorithm is very simple, similar to the bisection method. We start by being given a and b, which bracket a root for f of x. Calculate the slope of the line connecting f of a and f of b, and that's given by m is f of b minus f of a over b minus a. Then we calculate the point where this line crosses the x-axis, and you just solve for that, c equal b minus f of b over m. Now we want to check whether c is to the left of the root or to the right of the root. If it's to the left of the root, then it becomes our new a. If it's to the right, it becomes our new b. And the way we check for this, we check for the sign values, for the sign of the product f of a times f of c. You could check for the sign of f of b times f of c. It results in the same thing. Now, if f of a times f of c is negative, then that means f of c is to the right of the root, and that becomes our new b. Otherwise, c becomes our new a. And then check for convergence. If converged, return c. Otherwise, go to step 1. And in terms of Python, you just take the bisection method and define a new routine called secant. I'm giving you the code over here. Again, the secant method takes the function f and brackets a and b for the root, takes a tolerance and a maximum number of iterations, and does its thing. It implements the algorithm as was described in the slides. Now let's do our coding activity. That should be coding activity number 2. Should be coding activity number 2. Let's use the method of false position or the regular falsi method to find the drag coefficient for the parachutist to reach 40 meters per second in 10 seconds or 10 meters per second in 10 seconds. Same thing, we have this notebook already set up, and I have the falsi method already set up for you. All you have to do is execute it, and then now we call the falsi method just like we did before. We want to do for a velocity u0 equal 40 meters per second, and we call falsi, we call the residual function, and the brackets. In this case, again, if you look at the plot of the residual function for 40 meters per second, the root was somewhere between 10 and 20. So that's called Falsi, between 10 and 20, and 1e to the minus 5 and 100 iterations maximum. And you run this, you get it with 9 iterations. Compare that to the bisection method, which was a little bit less efficient than that, 10 and 20, 1e to the minus 5 and 100. It took 20 iterations for the bisection method to reach the same root. Now let's try it for u0 equal 10 meters per second. Falsi is going to be, so for 10 meters per second, again, we need to bracket the root, so we're going to go between 60 and 80, if you remember. 1e to the minus 5 for the tolerance and 100 iterations. And that gives us, actually it did not, u0 is 10 meters per second. There you go. And remember the bisection method, 60 and 80 and 1e to the minus 5, 100 iterations. Took 17 iterations to get there, whereas with the bisection method took 6 iterations, more than half, which is pretty interesting, which is pretty cool. Tells you that the regular method of false position, regular falsi, is much more efficient than the bisection method.